Good morning, ladies and gentlemen. Do you know who this is? If you don't, time to watch The Office. Okay. All right. So in class, I just gave you guys about 20 minutes to do the pairs quiz, and you are going to be grading this yourself. If you haven't done it yet, now is the time. You're missing out on easy points here. So if you haven't yet, if you're absent for whatever reason, do the pairs quiz. It's right above this video. Pause video, do it. And now that you've done it, let's go ahead and go over the answers. So just a reminder on how to grade. You're gonna give yourself 2 points for the correct work. If you're like, I don't know, just give yourself at least 1 point. Give yourself a point if some of it's right. 1 point for the correct answer, 1 point for correct units, 4 points total. And you'll be reporting your scores on the Google form below this. Okay. So for number 1. You should have that momentum equals mass times velocity, mass being 5 kilograms, velocity being 2 meters per second, and that gives us 10 kilogram meters per second.
2 points showing your work, 1 point for 10, 1 point for kilograms meters per second, 4 points possible.
4 points possible, okay. For letter 1B, you should have that the final momentum is 0.
2 points.
2 points for this one. Number 2 is 2 points possible.
Actually, B, it's B, 1B.
Oh, sorry, you're right.
So we got
1A, 1B, like that. There we go. For 1C, the change in momentum is final minus initial. So 0 is the final momentum.
Yeah.
Minus the initial momentum. Should be negative 10 kilograms.
By the way,
per second.
Mr. Boykin made a mistake here. That should be meters per second. Bad, Mr. Boykin. No biscuit.
Well, look at that. He got it right in the answer.
We got it right.
Yeah, I got lucky. Okay.
2 points showing your work, 1 point for the correct answer, 1 point for proper units, boom, boom, boom.
4 points possible. Letter D. The impulse.
What is the impulse? The impulse is the same as a change in momentum.
Same exact thing, so negative 10 kilogram meters per second.
2 points.
This one is out of 2 points. Okay, did you get the correct answer? Did you have the correct units? 1
Boom,
point
boom.
each. Right. Letter E. Jeez, let's go to the whole alphabet here. So impulse is force times the change in time.
We'll know the force.
Trying to figure out the force, we just move we divide by the change in time. Negative 10 over 10, we get negative 10 units. So 2 points for this, 1 point for this, 1 point for that. Letter E, 4 points.
And it's negative because it's in the opposite direction. It's slowing down.
Yes, yes, yes. That's very important. Okay. Number 2A. So you've got the 5 kilogram ball moving this way, and it's, remember when we were kicking the bowling balls, when you kick the bowling ball, we added an impulse of 10 newton seconds to that 10 kilogram ball. Is that right?
Yeah. Okay, so,
What was number 2? What did it ask to do?
well, that's what I was looking at. See, this is just the setup.
This is the set. Let me go to the next slide here. There. Oh, is that the right? That is the right answer right here. Let me go to the next one real quick. Oh, this is your, okay, this is your B, that's your A, right there. Okay, so this is how you should do it. What is the ball's, you see it right there? There's your answer right there.
Yeah.
Okay, so this one says, what is the ball's momentum after the impulse? So the impulse is the change in momentum, which is the same thing as final minus initial. Okay. And then we want to figure out what the final impulse is after we
Final
kick
momentum,
the ball. Oh, sorry,
yeah.
the final momentum. Thank you.
Yeah.
And so we can just add this over here. So you've got J. I'm sorry, not J. Impulse plus the initial momentum. Impulse, initial momentum. And we know that initial momentum is really mass times velocity. We're given this information.
Yep.
And this information.
And if you go back to that illustration on the previous one,
Impulse, initial velocity.
2 times 5 is 10,
10.
plus 10
Ooh.
is going to be 20.
It's gonna be 20. Look at that. Okay?
Boom, boom, boom.
So if you got this work right, this thought process right, give yourself 2 points. 1 point for the correct answer, 1 point for the correct units right there. So 4 points possible for, that was 2A. Even though it says B, 2A. Sorry. And this is 2B. 2B, what is the speed of the ball after the impulse? So we want to know what the speed is. We just divide by the mass. momentum was 20 newtons per second. Now, if you got the wrong answer for this, but you put your answer in right there, give yourself the points. Divide it by the mass, and you get your answer. And if you didn't get the right answer here because you had the wrong answer, give yourself some points.
That's right.
Okay, so if you got the right work here and you would have had the right answer, give yourself 4 points total.
All right.
So 2B, 4 points. So what does that make us our grand total?
4,
4, 5, 6, 7, 8, 9, 10, 11, 12, 13,
20.
14, 15, 16, 17, 18, 19, 20, 22, 23, 24. Is that right?
Yeah.
Okay. So out of 24 points, again, just report your score on the Google form below.
Yeah.
Okay, now for the good stuff. Law of conservation of momentum.
We had a conservation law before. That was conservation of what? That was conservation.
Of energy, right?
That's it. Yeah.
All right, energy at the beginning equal to energy at the end. And so it's the same idea, but this time with momentum.
Yeah.
The initial equals the final. Oh, I'm over there. There we go. So what the heck is momentum? What's happening here? Well, we have something that's happening before.
Yeah.
We have an event.
Yeah.
And then we have the after effects. Okay? And we need to understand that for the law of conservation of momentum, for a closed isolated system, the momentum before is equal to the momentum after.
Closed isolated means no energy coming in, no forces exerted in or out. Nothing leaves, nothing comes in. It's all just the things that you're talking about.
And what we do in physics is every time we have a problem, like I think on the next slide, we define the system and so it's closed.
Yep.
Okay, an explosion. So there's different types of examples of momentum problems. The first one we're going to talk about is an explosion. The momentum before, in an explosion, the momentum before and the momentum after is equal to 0.
But in an explosion, don't things go like flying?
They do go flying.
I wonder if we could have an explosion here in the
We can have an
classroom.
explosion. Let's do it. Okay, where's my handy dandy skateboard? Okay, so Miss Moore is not a skater. I don't know if you guys know that song. The Skater Boy, she said, "See you later, boy." You know that song, Mr. Morgan?
No.
Avril Lavigne? Okay. Okay, so here we go. So
How should we define our system?
our system, we're going to talk about an isolated system here. The system is teacher plus skateboard plus bowling ball.
All right.
Cool? And at the beginning, what is my momentum?
0. You're not moving.
Okay, I'm going to throw it that way. I'm going to move over this way a little more. Right there. I'm going to throw it that way. Okay, so I'm not moving.
Oh, the bowling ball went that way and you went the other way.
I went this way, and now I'm not moving. Okay?
Because of friction.
Yeah, because of friction. Good old friction. Okay, so
Now, that was an explosion. The momentum before was 0. I get that, but how can the momentum be 0 afterwards?
how can it be 0 after? Do I want to put it on the board right now?
Let's make a sketch.
Where is my erasers?
For those of you who wonder what Mr. Blicken looks like, there he is.
Okay. So, all right. So, I'm first just gonna draw skateboard and bowling ball, right?
Yeah.
So this is.
Shouldn't there be like little wheels on it? Doesn't roll without the little wheels.
Okay. All right. So here is our system, and at the very beginning, do I just want to say
Momentum is 0.
equals 0, right?
Yeah.
So momentum equals 0.
Yeah.
Right here. Okay. So this was before. Okay. Now let's talk about after. Okay. So what happens after? The ball is going this way with a certain velocity.
Yeah.
Okay, those are the holes of the bowling ball, in
Oh,
case
yeah,
you're wondering.
I can see that.
The artiste in me, okay? And Miss Moore plus the skateboard is going this way.
That arrow is too long for you.
Oh yeah, you're right. I didn't go that far. Beep, 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 beep.
And a longer arrow for the bowling ball.
It was more like this.
Because you were barely moving.
I know. The bowling ball was going was It's really moving.
Now the question is, how can the momentum be zero afterwards if you're moving and the ball's moving?
Well, I feel like maybe. Okay. So I'm seeing something here. So we've got little mass,
Yeah.
big velocity,
Yeah.
and we've got big mass, little velocity,
Uh-huh.
and they're going in opposite directions. So don't they cancel each other out?
Oh, you mean like positive and negative?
Yeah. So we've got. I'm gonna
So
call
which
this.
way should negative be?
I call this negative.
I like that.
I'm gonna make it red. So I've got this negative, little mass and big velocity, and it is going to equal green. Ooh, can you see the green? Green's over here. And I've got we'll call it a positive, big mass, and a very small velocity.
And if you add them both together, they make zero.
Yeah,
Since
so-
they're equal and opposite, one's positive, one's a negative.
It's gonna equal 0. Okay, sweet.
All right.
Good. Okay, so so whenever we have an explosion, they equal 0. Bada boom. Okay, so let's make a sketch. Oh, perfect. We can just add stuff in here. So the mass of the bowling ball is 7.5 kilograms.
So then you could put that right under the MV there.
Right here.
Yeah.
I'll just use black. 7.5 kilograms, and this is going to be a negative.
And the velocity of the bowling ball is negative 4 meters per second.
Negative 4 meters per second. I'm going to get rid of this negative right here because that negative
That'll do it.
is right here. Okay. Equals, and then the mass of my me is 65 kilograms. And the mass of my velocity, I'm sorry, and my velocity is what we're trying to find. The
Yeah.
mass of my velocity. Okay.
The T plus S is teacher plus skateboard.
I'm gonna put that in there. It's actually really important that because we've got two velocities right here,
Yep.
right? Okay, so how do I solve for this?
Divide by 65.
65.
Does that go away?
Teacher plus skateboard equals. Okay, so 7.5 times negative 4 divided by 65, and I get negative 0.4. Oh, negative. Oh, no, what I forgot to do. So I get a negative 0.462. That is not right. Right, because the negative sign?
Okay, so
So you know what?
here's what we did wrong. You have to do the momentum before is equal to the momentum afterwards. It has to be 0. So what you've got is before the momentum is 0, and afterwards it's the momentum of one plus the momentum of the other. So you've got to have
Let's put
P.
it like this.
P is equal to P prime,
P
P prime.
plus P prime, like this?
and yeah, just P prime.
Oh, yeah. You guys, this is a great example of how to think through.
P prime, and before this is 0. Put 0 right there. 0, and that equals P bowling ball afterwards, plus P teacher plus the skateboard afterwards. Put the little afterwards up there
Include that, okay?
and for both of them.
Oh, thank you.
All right, so now what that means is how can you add two things together and make them be 0? One has to be positive, one has to be negative. So what you did, see you've got the negative over here? Put the negative in
He's
front
right
of it
there,
again,
okay.
yeah.
Okay, so what we are realizing is, okay, so we know that the momentum of, at the very beginning is 0.
You were just
right?
standing there.
So at the very beginning, it's 0.
Yep.
And the momentum at the end after is the
total momentum, the sum of the momentums of the two
Is gonna
has to
be
add up to 0. So that
bowling
means
ball plus
one of them's
teacher.
negative and the other one's positive.
exactly.
And like you said, they have to cancel each other out.
And we're gonna make this one negative and this one positive. And notice how I got an answer that didn't make sense.
Yeah.
And so we have to go back and look at it. And so what happens is we have to include that negative here.
So if you
So-
put the negative, that makes your answer.
Positive.
Negative times a negative is a positive.
So 7.5. Oh, I'll put the negative in there for yours. Negative 7.5 times a -4 divided by 65, and then we get our 0.462.
So 0.462 is not very fast, and that's realistic because you were not going very fast.
Yes.
So that's an explosion where before the momentum is 0 and afterwards it's 0. And how can it be 0? Because they're going in opposite directions. One's positive, one's negative. They cancel each other out.
Yeah, and if you are confused by this, just realize that Miss Moore can't have a negative velocity because the velocity is the direction, right?
Yeah.
And if I'm going this way and we have deemed that the positive direction, it doesn't work,
That's
right?
right.
So you realize you messed up on your side somewhere, and we know that these two have to be equal and opposite. This has to be a positive, teacher plus skateboard, me.
Yeah.
And then the ball has to be negative. So okay, all right, moving right along. Okay, why do rocket motors work in space? Doo-doo-doo. Hence the rocket, okay?
So if you turn it around the other direction, it'll be kind of like what you were doing.
Like this?
Yeah, because you
yeah.
got the far. The
Oh, that's
far,
right,
the
right.
far come out the back of the rocket, come flying out.
So you've got this rocket in space just chilling here, and how do we get it to move? It's a vacuum. There's no air out there. It's
You push the button to make a far come out.
ding, right? And so the as Mr. Boykin is talking about the fart coming out, those are like little mini bowling balls, right?
Oh, yeah.
And what happens is the rocket is like Miss Moore and skateboard. A little fart, the gas that comes out, the explosion is like the bowling balls, and they explode. They move in opposite
And
directions.
what is fire anyway? It's like little gas particles at high energy,
High
right?
speed. And you guys, we just finished our fourth section a while ago, and there was a question about why a firework works and how come this works. Well,
Yeah.
forces come in pairs,
That's
right?
right.
Equal and opposite. So
Equal in magnitude, opposite in direction. So the force pushing on the bowling ball equals the force pushing on the rocket.
and it makes it move. Okay. I think this is our last one. Do we want them to do this as homework, or do we want to probably do it with them?
Well, let's make a diagram, put all the stuff on there, and then, I wonder here, I want to take, it says page 200.
I almost feel like we should do this with them because we haven't done one. We haven't done we should probably do another practice problem with them.
Oh, this is in the book.
It is.
See, an astronaut has got a rocket gun. He's just sitting there. His velocity is 0. Afterwards, the fire shoots out of the rocket gun in that direction. The astronaut goes the other direction. Okay.
So 84-kilogram astronaut fires a rocket pistol that shoots. There it is. That shoots. This is the mass of the astronaut.
Yeah. Well, that's before. That's where everything's just sitting there.
Yeah. And then the mass. I know. The mass of the
So-
gas. Is it 875?
875 meters per second.
Oh, meters per. That's sorry. That's not mass.
See, it's 0.035 kilograms of hot gas. So make a second diagram over here showing the pistol going off.
Oh yeah. Okay. So I'm gonna say that the dude is gonna go this way.
Yeah.
With the thing in his hand,
and
right?
show the fire coming out.
Yeah, and this stuff is gonna go this way.
Yeah.
That direction.
Okay. And
Okay.
so the mass of so that's 875 meters per second.
Sorry, the mass of the pistol is 0.035.
Well, that's the hot gas that comes flying out.
Oh, I'm sorry, I'm not reading this question. An 84-kilogram astronaut fires a rocket pistol that shoots 0.035 kilograms of hot gas at that much speed to the left.
How fast and in what direction does the astronaut move? Well, the astronaut's going to go in the opposite direction.
Yeah. So the velocity of the gas at the very end it's going to be. I'm going to call this the negative direction.
Sure.
Negative 875 meters per second. To the left, and we want to know what the velocity of the astronaut is.
So we got to do the
This way.
momentum before is equal to momentum afterwards.
Yeah. Momentum before is equal to the momentum afterwards. Oh,
Before the momentum is 0.
yes. Before, so 0 equals
Momentum of the gas
momentum of
afterwards.
gas plus
momentum of the astronaut
the momentum of
afterwards.
the astronaut afterwards.
Put
Okay.
put the little primes there after the.
Oh yeah, I always forget to do that.
That's
It's
all right.
important to write those in there. Okay.
So where does the answer lie in this equation right here? What are we looking for? We're looking for the
The mass and the
velocity of the astronaut. So we
So
need
the-
to solve that for the momentum of the astronaut. You subtract by the momentum of the gas, right?
Yeah, so I'm gonna go ahead and subtract this guy on both sides, right?
Yeah. Things
Okay.
can go away.
Left cancel. So I've got negative equals. Now this should look familiar, right?
Yeah.
Okay. And this is what we were missing before.
Yeah.
We were forgetting that negative sign, right? You guys are like, oh, that makes sense. Okay.
So now we've got the mass times velocity of the gas is equal to the mass times the velocity of the astronaut. Mass of the astronaut, velocity of the
And
astronaut.
what are we trying to find here?
The velocity of the astronaut.
Okay. So I'm just going to go ahead and divide by the mass of the astronaut. Divide by the mass of the astronaut. And this is the mass of the
Gas,
Of the,
yeah.
I keep saying the pistol, like gas right there. Gas right there. And let's go ahead and plug it in. Okay, so I've got negative, and the mass of the gas was 0.035 kilograms. And the velocity was, oh, Miss Moore's running out of space. The velocity was
875.
negative 875 meters per second. Do a better job with your spacing. And the mass of an astronaut was 841 kilograms.
84 kilograms.
Oh, 84 kilograms. Okay. Yeah. All right, let's do this. So I've got negative 0.035 times negative 875, and then I divide it by 84, and I get 0.365.
It's not very fast.
Nope.
So the velocity of the astronaut afterwards is 0.365. Now I'm going to
what
go
else am I talking about here?
over here to the book. 0.36 meters per second in the positive direction.
Okay, so
And so the important thing is momentum before is equal to momentum afterwards.
and if I could, you know,
The momentum before is 0.
if I could redraw this, if I had read the question more thoroughly, what I probably would have done was put my masses on this side, just to
Yeah.
have everything in one spot. So I would have gone mass of the gas equals 0.035 kilograms, and then mass of the astronaut equals 84 kilograms.
Yeah.
And this question is asking us about momentum, right?
Yep.
And it probably would have been a good idea if I said the momentum before was 0, and I said momentum after equals momentum of the gas plus momentum of the astronaut. And then,
And that equals 0.
yeah, and you can see the 0 goes here, and then this goes here. So the biggest takeaway here is that with an explosion, this right here is what you need to understand.
That's right.
And that leads us to this. Don't forget your negative sign there. And well, it's not about forgetting. Just, you know, do the math, walk through it. Okay.
It's simple, actually.
It is simple.
You just need a little practice. I think we should give them some practice.
We should give them some practice.
Is there practice coming up here?
There's no practice.
There's no practice?
We
Well,
should probably pick some practice for them to do.
we'll think of it and get back to you.
We'll put it on there.